So I'm Rupesh Kumar and welcome to today's session on welcome to today's session on linear algebra to geometry, right? So let us wait for a few more minutes and then we can start the session. Fine. Okay. So hi everyone, let's start today's session on this on linear algebra, right? So happy Independence Day, everyone. So I believe some of you are in the will be looking into this video after this session recording is uploaded on YouTube. So yeah, let me start the session assuming no one is here, right? Okay, fine. Oh, yeah, let's start. So in this week, what you guys have seen is some linear transformations in and linear transformations, right? Some basic linear transformations. So first idea was what is so first let's start with what were the topics covered during this session. So let me add a page. Right. Mhm. Okay, fine. So the topics that were covered is topics covered. So the first thing that you saw is uh, l- everything was done in 2D. So we are dealing with all the concepts in 2D space. And we have first thing is lines, right? How to represent lines, what is the parametric form for lines, right? So then what are linear maps in 2D? So linear maps in 2D. Then again revisited some linear systems, right? Revisited linear systems. And then the last you saw eigen what are some there is some properties of matrices that can be derived using eigenvalues and eigenvectors, right? So these were the few things that you saw in this session in this week's sessions, right? So a brief introduction to the parametric part, right? So yeah, so okay. So let's say, yeah, so in the last session also I solved a problem related to this itself. So let's say if you have a point, 2 points P and Q, right? And you want to in the 2D Cartesian plane. So for example, this is our 2D Cartesian plane and we have 2 points. Let's say point one is P here, point Q is here, right? And then when you want to draw a line between these 2 points, right? You can always draw a line between these 2 points, right? Point P and Q. And how can you represent that line using linear algebra, right? So the first idea is you can always draw a vector going from point P to point Q. You can always represent this as a vector V that goes from P point Q, and V can be computed as the coordinate values of Q minus the coordinate values of P, right? So let's say P was 1 comma 1, P was 1 comma 1, and Q was, let's say, 2 comma 2. So you can always write V equals to 2 comma 2 minus 1 comma 1. To 1 comma. So P is a vector that starts with origin and starts at P and points in the direction 1 comma 1, right? Now let's say if you want to define all the points present on this line, what you can do, you can use the parametric form, right? You can always write any point R, let's say vector R, that vector any point. So this was our vector P V, right? Now you can always define uh any point in between P and Q, right? So let's say I want to find the point, some point here that is at a distance, let's say T, distance T from point P. So you can always say what will be the point. So the point would be P plus T into V. So this is known as the parametric form of the line, right? Parametric form of the line, right? So this is how you parameterize lines using in 2D Cartesian plane if you know the coordinates, right? So, right. So basically, this is a parametric form of a line. So how can you define this? Any defined line, like what is the parametric equation? Parametric equation is line at distance t from point P is defined as P plus TV, where T is a scalar, right? P is a point and V is a direction, right? V gives you the direction in which direction you can move to get the points, right? And there were few definitions. If the point if the computed point lies in the, let me check this, yeah. So if the point computed point lies in the middle of these 2 points, then the combination of P and Q is known as linear combination. Now let's say if you want to extend this line to some other point, then the value of T will be greater than 1. In that case, it won't be a linear combination. Essentially, it will be an extrapolation of this line, or if t is less than 0, then this will again be a extrapolation of the line. Fine. So these are something. Now, what are the unique things to define this point? So there are a few properties, like if you want to define the equation of a line, what you can do, you can give two vectors, right? P and Q, that defines the line, or you can give the origin and some direction D, V, right? You can always, yeah, you can define the points P and Q and define the line is going in this direction from or originating from P, or you can give P and some direction by the vector V, right? And then which is parallel to the line, or even you can in 2D you can always say, you can also give a line that is perpendicular to the line that we are trying to draw. So from here also we can infer that the line has to go in the perpendicular direction from this point line, right? So these were the ideas, right, of how to define lines. Then what are linear maps? So basically linear maps are nothing but in two-dimensional Cartesian plane, you can transform lines, any map, any function that maps lines to lines is known as a linear map, right? So let's say you have in the 2D space. So let's say in the 2D space, let's say in the 2D space, you have a line like this, right? You have a vector that goes from here to here. Now you do some operation on this, some transformations, apply some function to it, and it becomes something like this. So it rotates and gets scaled. So then this is a linear transformation because the line is a line. Now let's say there was a mapping that takes this vector and transform this into this kind of stuff. Then this is a non-linear mapping, right? Non-linear, because lines are not mapped to line, but this is a linear map. Fine. I hope my screen is visible and I am audible. Okay, in the beginning. Now, now I guess others have joined. So yeah, anyone please confirm by typing the chat box if I'm audible and my screen is visible, and I will also explain. Fine. So everyone please confirm if I'm audible or and my screen is visible. Hello. Am I audible, everyone? Please confirm. Anyone, please confirm. Okay. Just type in the chat box to confirm. So no one is responding. I'm not sure if I'm audible or not. Yeah, yeah, great. Thanks. So these are the rules for these sessions. Basically, you all, if you have attended the previous sessions, the rules are same. So I will be explaining some problems related to the topics covered during the week. And if you have any doubts at that moment itself, you can type in the chat box to ask for your queries and doubts, right? So this is the same pattern that I'm following today also, right? So let's resume the session. So this is, I was just giving a brief introduction about what were taught in the previous lectures, right? Then some linear. So this is kind of a mapping. We will see how through the problems, right? Then linear systems. You again went back and understood about what are homogeneously systems of equations, right? Homogeneous system of equations and what is the meaning of the solution, how to get the solutions, right? And in the last, you will see about eigenvalues. These are something new that we will be looking into today's session. Fine. Okay, so let's move on to the first problem for this week. Let's start. So let p equals to 1.2 and 3 q equals to 3 comma 5, right? What is the distance between the 2 points, right? So let's take up the Cartesian plane here. Fine. And we have the points 1, 2, 3 here. This is the x-axis, this is the y-axis, right? And then 1, 2, 3, 4, 5, right? So point P says 1 comma 2. So this is 1 comma 2. You get this point P, right? And then point Q says 3 comma 5. So this is 3 comma 5. It goes here, right? Now what is the distance between these 2 points? Fine. So we want to find the Euclidean distance between these 2 points. How to find the distance between these 2 points? So the easiest way, using your matrix algebra that you have, I mean, sorry, the 2D coordinate geometry that you have should have been studied in your class 12th, right? You must have seen this in class 11th lectures also. You can solve this problem simply. Fine. How you can do this? You can use Pythagoras theorem, right? You know that. Fine. Yeah. So you know that this distance is essentially what? This is 2 and this is 2, 1 comma 2 and 3. This is 3, right? 3 comma 5 and this is 1, right? So basically this distance is 3 minus 1, which is equals to 2. Now again this distance is 5 minus 2, which is equals to 3. Now you can apply the Pythagorean theorem and you get the answer that the length is 9 plus 4 square root, right? 9 plus 4 square root, which is root 13 is the answer, right? So this is the way. If you solve this problem without using any new knowledge in the linear algebra that we have learned till today, right? But let's go ahead and try to solve this problem without using this information. The result will be same, but yeah, let's do this since we are in a linear algebra class, so we should know this. Fine. So let's start with the first way. First way, you can always define a line between the points P and Q, right? You can define a line between points P and Q using the vector, right? You can always define this vector. So line will be given as line of t equals to P, vector P plus t into point P plus t into vector Q minus P, right? Now you can write this as P is basically the point P is 1 comma 2 plus vector Q minus P would be 3 minus 1, which is 2, or 5 minus 2, so 2 comma 3, right? This is the direction and this is the origin. Now what is the length of this line between the points P and Q? What is the length? So basically length of the line, sorry, line between t equals to 0 to t equals to 1, right? What will be the length? This will be equals to the length of vector vector that goes from going from P to Q, that is Q minus P, right? So if you put T equals to 1, uh, you will get basically this quantity, right? Hmm. So now how to find the length of this vector? You know the dot product idea, right? You can find this using dot product, right? So what is the vector Q minus P? This vector is 2 comma 3. So what is the length of this vector? So let's say if you have a vector like this, vector V, that looks like this, and you want to find the length of this vector, what you can do, you can take its projection on itself using dot product. Okay. So you can always find the length of this vector by taking its projection onto itself. So let's say the idea looks like this. So let's say you have a vector that is this. So let's say this is a vector, right? So let's say this is a vector, right? This vector is, let's say, 2 comma 0. Then what is the dot product of 2 comma 0 with itself? 2 comma 0 dot 2 comma 0 is essentially 4, right? And this is essentially equals to length of vector squared. This is the length of the vector squared. So this is the dot product. So you can always find the length of vector as square root of this, which is 2, right? So yeah, so let's do this. So length is equals to square root of 2 3 dot 2 3, which is essentially is 2 to the 4 plus 3 to the 9, which is essentially root 13, right? So this is the answer that we were getting using the Pythagorean theorem that from the knowledge that we all already had before this lecture classes. But now we can use this property of vectors dot product to find the length of the vector. Fine, everyone. Do you have any doubts in this problem? Please type in the chat box. So in this problem, we saw that how to define a line between 2 points on the Cartesian plane, then how to find the length of that line using dot product. So basically, dot product gives you the length of the projection of a vector onto another vector. Now, what is the length of projection of a vector onto itself? Essentially, its length squared. Anyone, do you have any doubts in this problem? Please type in the chat box, or we can proceed with the next problem. So no one has any doubts, right? So let's move on to the next problem. For what values of scalars C1 and C2 is the vector W equals to 6 comma 4 a linear combination of U 1 0 and V 4 comma 4, right? So for this, you need to understand the concept of linear combination, right? What is the meaning of linear combination of U equals to 1 0? So U is a vector and another vector V equals to 4 comma 4, right? Right. So what is the meaning of this linear combination? This essentially means hmm, yeah. Hmm. So what does linear combination mean? So let's see this in the Cartesian plane itself, right? So you had this Cartesian plane, right? And you have a vector 1 comma 0, right? So let's take this vector u. This is your vector u. And then let's take the vector v, which is 4 comma 4. So 4 comma 4 goes somewhere here, right? So this is vector v. So what is the meaning of linear combination of these vectors? This means essentially multiply a scalar to both vectors and add them, right? This means this essentially results in a linear combination of linear combination. This essentially is the definition of linear combination of the two vectors, right? So now how to so now this is the definition of a linear combination. Fine. So you are only allowed to scale the vectors by some amount and add them up. So this is the definition of a linear combination. Fine. So now, so if we know the definition, so from here I am saying I have to find the linear combination of u and v. So let's say I associate the value c1 with the vector u that is already given in the problem, right? And c2 is associated with the vector v, right? Now, if I use these scalars as a linear combination weighted, so c1u plus c2v, I know we get the term w, which is 6 comma 4, right? We get 6 comma 4. So what is the value of c1 and c2, right? Fine. Let's go ahead and solve this. So this essentially means, so what does this mean? This means, let me write this c1 into 1 comma 0 plus c2 into 4 comma 4 is equals to 6 comma 4, right? From here you can say now what you have to do, you have to simply solve this linear system of equation. You have to build some linear system of equation from here and then solve this. How to build that system of equation? So now when you look at these terms, you can say this let's look at the left hand side term, right? Left hand side term, you will see it will be scalar multiplication with a vector plus scalar multiplication with another vector and add them up, right? So it becomes c1 into 1 or c1 into 0. So this is the vector sum, right? So first I multiply the scalar with the vector. So this is the definition of a scalar vector multiplication. Now I do addition of two vectors. So I get c1 plus 4c2 and c4c2, right? Now the RHS says that this vector is essentially equals to 6 comma 4. Now if you compare LHS equals to RHS, you get, so this implies C1 plus 4C2 equals to 6 and 4C2 equals to 4, right? Now you want to solve these systems of equations 1 and 2, right? Now you go back to the knowledge that we already learned in the first week where we were solving systems of equations. Now this is a very two equations. We have two linear equations, right? Two linear equations here. And we have two variables, two unknowns, right? Two unknowns. We can solve this. So from equation 2, we can say C2 equals to 4 by 4, which is essentially 1. And then using this, put this information, put this value in 1 to get C1 plus 4 into C2 is 1 into 1 equals to 6. That gives us C1 equals to 2, right? So the values of C1 and C2 that gives that when multiplied by U and V gives the results in the linear combination resulting in 6 comma 4, right? So therefore, for C1 equals to 2 and C2 equals to 1, we get C1U plus C2V is equals to W, right? So this is the solution, right? So in this problem, what you had to do, first you have to understand the definition of linear combination. What is the meaning of a linear combination? And then from there, you can build up the system of equations using properties of matrix product. matrix is a vector product with a scalar, and it's a definition of summation of scalars. And finally, you can build up this linear system of equations that you can solve very using various ways that you have known. The first easiest way is what I did here. I simply use substitution, right? You can always do Gaussian elimination. You can build up the matrix A, or you can build up the augmented matrix and solve the system of equation, or you can always find the inverse of the matrix system for finding the solution of these equations, right? So I don't need to explain that here, but yeah. So this is the solution. Now what I want to do, I want to give a geometric view of this geometric interpretation of this problem, right? So let me take the Cartesian plane here. Okay, fine. We were here, right? So let me give you a geometric interpretation of this problem, right? Okay, fine. Now you have vector u as 1 comma 0. So vector u is 1 comma 0. So this is vector u, and vector v is 4 comma 4, right? 2, 3, 4, right? Fine. So this is your vector v, right? So this is your vector v, and you want to get to the you want to find a linear combination of these two vectors to get to 6 comma 4, right? 6, right? So 6 comma 4 will be this vector, right? This is the point here. Yeah, good. So this is the result that we want to achieve, right? Hmm. So this will be the vector W, right? So what are the linear combinations that we can do to get here, right? So the our answer says C1 has to be 2. So you double U by amount, right? So you get 2 times U, which is essentially this vector 2 times U. Now this is, so this vector is 2 times U plus 1 times V, right? So this plus this. So how to do this summation? You do the parallelogram rule, right? So you draw this parallelogram like this, 2, 3, 4. So you draw this parallelogram here. You know how to do vector addition, right? So the result will, the point, the summation will be the point where the parallelograms along the diagonal of the parallelogram, right? And then this will give you the vector W. So right, when you look at it through vector summation, you also get the same answer. So our answer is correct. So I am just saying take 2 times U and add it up with the vector V. You will get the vector W as your answer, right? This is evident in this figure. Fine. Anyone, do you have any doubts for this problem? Okay, I believe no one has any doubts. So let's move on to the next question. So anyone, do you have any doubt? Just keep ask me in this chat box, right? Okay. So let's start with the third problem. So let u equals to 2 comma 3 and v equals to 3 comma 4.5 and w equals to 2 comma 3, then which of the following is true, right? And again, this problem is saying we have to take the linear combination of the vectors u and v, and the scaling weights should be c1 and c2, right? So the question is saying we want to observe what happens when we do this c1u plus c2v, right? and I want to set this equals to W. So let's go to option A, right? So this is option A. So option A, this asks us what happens when we set this system of equations? What is the solution to these systems of equations, right? Hmm, right. So let's try to build up the matrix here. So now in the previous problem, what I did is I used the simple fundamental rules to build up the system of equations and then solved it. In this problem, what I will be doing for defining these linear combinations, I will be using some advanced information from linear algebra that will be helping me out in solving this problem very easily, right? So this will be give me an intuition on what matrices essentially are, right? So let's say if I write up a matrix that looks like this, let me build up a matrix A that essentially looks like this. The vector u as its first column, right? Vector u as its first column and vector v as its second column, right? So let's fill this matrix. So this essentially looks like 2, 3 as the first column and 3, 4.5 as the second column. And let's define a vector x, right? Vector x, right? Let's define a vector x that essentially is a column vector containing the entries C1 and C2. Then what will the value of AX, everyone? Can you say this? What is the result of a matrix vector product AX? This, so how to write this? This is essentially 2, 3, 3, 4.5 into C1, C2, right? So the first column was U and the second column was V, right? So what is the result of this matrix vector product? This is essentially C1 into column 1 plus C2 into column 2, right? So this is essentially representing C1 into U plus C2 into V, right? Now this has to be equals to W, which is equals to, what is the W here? 2 comma 3, right? 2 and 3. It's a column vector 2, 3, right? Starting from origin and going to the point 2 comma 3. So this is a column view of the matrix multiplication, right? Matrix vector multiplication. So there are two ways you can finally get to the same result of doing matrix product. One is the simple way that you choose start each row. So row 1 into column 1. You take the dot product of row 1 and column 1, row 2 and column 2 and so on. This is how you were doing the matrix vector product or matrix product earlier, but now you have another way of looking at this. So essentially, when you do matrix vector product, you can always say entry 1 of the vector into column 1 of the vector matrix plus entry 2 of the vector into column 2 of the matrix. And you will see that this and that way will give you the same result. You can always verify that this is the same result. This gives the same result. Now I can always write the vector W here, which is 2 comma 3, right? And we saw a very beautiful property here. So if you want to take linear combination of two vectors, you can always rewrite. So you can always rewrite this equation. Let's call this equation 1. So you have then this equation 2, right? This equation 2 is equivalent to equation 1, right? So this is a beautiful way. If you want to take linear combination of two vectors, you can always write them as a column vectors of a matrix and then write the scalars as a vector and then write it as a matrix vector product. Now the question is, now we have built up a different same system, same concept with a different way, right? And now let's try to solve this system of equations. So the system of equations looks like this: 2, 3, 3, 4.5 multiplied by C1, C2 is equals to 2 comma 3. Now can we comment on the number of solutions of this problem, or can we solve these systems of equations, right? So the thing is, we can solve this systems of equations. Number one easiest way is substitution. You can do substitution. Again, I'm reiterating these things that you can use different ways to solve the system of equations. You do Gaussian elimination using this substitution itself, right? Gaussian elimination. Third way, you can reduced row echelon form RREF using elementary row operations, right? Number 5, you can always number 4, you can always define in the over the augmented matrix, right? Over the augmented matrix. Number 4, you can use the inverse of matrix A. You can find inverse of A, and then solution would be x equals to A inverse B, right? These are few ways that you can use to solve these systems of equations, and also comment on the properties of this matrix, right? There is another way. You can also do Kramer's rule, right? You can always use the Kramer's rule, right? That will also give you the solution to the systems of equations. So these are the 5 ways that you can use to solve these systems of equations. All of them essentially reduce down to same thing and result in the same answer, right? So again, we are not interested in what is the solution of the systems of equations, but we are mostly interested in what will this system of equation look like, right? What will the solution looks like? So option A says there exist infinite many values of C1 and C2, right? So anyone, can you help me out in solving this answer, in giving the answer to this problem? So if you look at this system of matrices Ax equals to B, can we comment how many solutions will this system contain? Like how many values of x will satisfy these systems of equations? Anyone, please help me out. Can you tell me how to how can we say? Just give me an idea like how should I proceed? Now let's say if I have these systems of equation, what should I do? I just want to comment on how many solutions this system has, how many values of C1, how many pairs C1, comma C2 will satisfy these systems of equations. Can I do this? Even if is it even possible or not? Anyone? Am I audible? So please type in the chat box if you want. I'm also allowing you guys the mic, right? If you want to speak, you can speak also. Fine. So someone is saying C2 equals to 0. Yeah, you are basically trying to solve the systems of equations. My question is, um, can you comment on the solution of this? How many solutions this will contain? So let's say you are saying C1 equals to 1. So I can see that C1 equals to 1 and C2 equals to 0 is one set of solutions. Are there any other solutions? Are there any other sets of other pairs, right? Other pairs C1 commas C2 that satisfy these equations. Are there any other sets? The question is this, can we comment on this? So you had already learned about this in the first session itself, right? So whenever you try to solve a system of equations, you can have at you can have one solution, right? This is the one solution case. You can have no solution. So this is a no solution case, right? The lines are parallel, and you can have infinite many solutions, right? When the lines are coincident, so line 1 and line 2 both are on the same line, right? One solution in, yeah, and zero solutions here, and here infinite solutions, right? So these are the three cases that you will observe when you try to solve a linear system of linear equations, right? So let's look into this and try to identify from here. So do these two lines intersect? So let's look geometrically, right? So one line is along the vector u, which is passing through origin and 2 comma 3, right? So 2 comma 3 here. So this is for the first line that goes along the vector u. Then the second line is 3 comma 4.5. So 0 to 3 comma uh, 2 comma 3, 0 1 2 3 comma 4.5, somewhat here, right? And this goes like this, right? Fine. So this is for a homogeneous system of equations, right? Though just ignore the axis here. So let me remove the basis here, right? So these can be your two lines, fine, depending on the this b value of b. So you are getting exactly one system of equations, right? You do not get multiple solutions, one solution, right? So this is the correct answer for this. You have only one solution. This is not the case where you are getting they are parallel or they are coincident. No, no, right? So only one solution exists. So option A is wrong, right? So how this is one way you look geometrically. You plotted the lines and see how it look like. Another way is you can always check if the matrix A is invertible or not, right? So if the matrix A is singular, then you can have infinite many solutions. Fine. And if the right. And it's a homogeneous system, right? Then only you will get this. Okay, fine. So this is how you determine. So if there exists only one value of C1, C2 such that C1 equals to 0, C2 equals to 1. No, option B is also wrong, right? So when you say 0u plus 1v, let's look at option 2. So you say 0u plus 1v. So what will this be the answer? 0u plus 1v. 0u plus 1v is essentially 3 comma 4.5. No, option B, C is also incorrect. Option B is also incorrect, right? Option C, there exists no C1, C2 such that this happens. No, this is also wrong. And U and V are linearly independent vectors, right? Option D is correct. Option D is absolutely correct. So option D is the correct answer for this problem. Okay, fine. So let's see if I'm right also because I think this is wrong. Okay, so there is one thing that I forgot to look into here is you can always so there can be multiple solutions to this problem, right? Why, how this will happen? Let me show you, right? How to get multiple solutions here. So let's look at the determinant of the matrix A, which is essentially 2 into 4.5 minus 3 into 3, which is 0. This essentially means that the matrix is singular. That is, the vectors 2, comma 3 and 3, comma 4.5 are linearly dependent, right? So how to look into this? So just do one thing. So take up the matrix A, which is 2, 3, 3, 4.5, and try to find the row reduced row echelon form, right? So try to form the RREF of this matrix, RREF, right? How to do this? Just say R2 is equal, replace R2 with 3 by 2 in, sorry, R2, replace R2 with R2 minus 3 by 2 R1. What is this value? This is essentially equals to 3, uh, 4, 3 comma 4.5 minus 3 by 2 into 2 comma 3, which is essentially 3, 4.5 minus 3 and 9 by 2, which is essentially 4.5, right? This is 0, 0, right? So when you do this operation, you get the RREF as 2300, right? And then you want to solve the system of equations again. Now, when you set, now you can set C2 as any value, right? C2 can be 0, C2 can be 1, C2 can be 2, C2 can be this into this. Okay, wait a minute. Right. So now, so yeah, I should have included the augmented matrix here also, right? So augmented term will be here, let's see, 2 comma 3. Yeah, 2, 3, right? So you get here this, and you are trying to solve the system of equations. So 3, 4.5 and 3 minus 2, 3, 2, right? Again, this will essentially become 0. 3 minus 3, 0, 4, 5, 0, and 3 minus 3 by 2 into this. Again, 0, right? So you will get 0, comma 0, comma 0. That implies the RREF looks like this. For the augmented matrix, it looks like 2, 3, 2, and then 0, 0, 0, right? This multiplied with, so now this gives you an idea on the solution, right? 2, comma 0 is a solution, or is it? Okay. Okay, fine. No. This is not the solution, right? You want to make this left hand side as identity. So you don't get any way of proceeding further. You can't proceed further. No pivots exist from here, right? No pivots exist from here. So you could have infinite many solutions also, right? So this one way we saw this through your determinant. You can see the determinant of the matrix is 0, right? Another way, you simply plot these vectors and see how they look like. So let me do this. So u is 2 comma 3, v is 3 comma 4.5. So u can be written as u is a vector from 0 comma 0 origin to 2 comma 3, right? So let's draw this. This is the origin 0 1 2 2 1 2 3. So this is vector u, right? This is vector u, right? Let's draw vector v. Vector v goes from 0 0 to what was this, 3 comma 4.5, right? 3 comma 4.5. So 0 1 2 3 0 1 2 3 4 4.5, right? Here. Fine. This will go here, right? And then you can see that these two, this is the vector v. So they are basically uh, linearly dependent, right? They are linearly dependent. When you do this, when you plot this, you will see that these are linearly dependent set of vectors. So you will coincident vectors, so you will get infinite solutions, infinite many solutions. Yeah. So the correct answer would be option A, right? I just look at the wrong option. Yeah. So they are linearly dependent. You will get infinite many possible solutions. Anyone do you have any doubt? Okay, yeah, it was 4.5, right? Yeah. So 4.5 point would have been here somewhere. Right. So when you now draw this line, you will get coincident line on you. So you can see this geometrically also that they are coincident. So this system has infinite many solutions. Anyone do have any doubts? So there are various ways to know the number of solutions, right? So only three cases can arise. You could have one solution, you can have zero solutions, and you can have infinite many solutions. One solution if they intersect at a single point, infinite zero if they are parallel, and infinite if they are coincident. Now, how to check for these cases? You can check for the matrix A, properties of the matrix for while solving this system of equations, or you can simply draw the lines in the Cartesian plane and you can see if they are coincident, then you get infinite many solutions. This is what you are getting. Anyone do have any doubts? Please type in the chat box. Okay, so no one has any doubts. So let's move on to the next question. Which one of the following sets is a linearly independent set of vectors? Right, again. So again, what we can do, we can draw this line and see. Let's simply check, right? Fine. So set 1 contains the vectors 0, comma 0. So this is not a vector, right? Option A, and this is a 0 vector, right? And then 1, comma 3. Whatever you want to do, but this is not a vector, so you don't choose this. You can't choose this as an answer, right? So because also the first thing 0, comma 0, the vector 0, comma 0 lies on the vector 1, comma 3, because 1, comma 3 goes from 0 to 1, comma 3. So this is not the correct option. Option B, 1, comma 1, 1, comma 2, and 1, comma 3, right? So let's check. So 1, comma 1 is this, then 1, comma 2, right? So 1, comma 2 is this vector, and 1, comma 3 is this vector, right? So these are the three vectors and they are not coincident. So they are linearly independent, right? This is 1, comma 1. This is 1, comma 2. This is 1, comma 3, right? This is 1, 3. Okay? Right. Option C, 1, comma 1. If it has only one vector, so it has to be linearly independent. Option D, this is not a vector. This is the point origin, right? Anyone do you have any doubts in this problem? Please type in the chat box. It seems no one has any doubts. Am I audible? Great. So I think no one has any doubts. Let's move on to the next question. So let's u and v be two component vectors. Then what is the length of u comma v? U plus v, right? So this is the u L2 norm, right? This is L2 norm operator basically. I hope you have seen this in the lectures. And this quantity is essentially dot transpose dot raised to power 1 by 2, right? Again, we are dealing with 2D. So the property we want to look into the length of the vector u plus v. What does this look like, right? So option A says, what does option A says? This is essentially equals to u. Option A says u norm u plus norm v always. Is this true? Is this true? Let's think of this for a while, right? So let's say we have a vector u, right? And then we have a vector v. like this. And I want to comment on the length of the vector u plus v, right? So now first you do the vector sum, right? So first you do the vector sum, and this is the sum that you will get, right? This is the vector u plus v, right? So now let's do one thing. So let's look at using geometry, and then let's look at using linear algebra, right? So using geometry, right? So let's take out this section. Let's take out, oh, sorry. Let's take out this section of this summation, right? Let's take out this. So you can take it out and put it like this. So this is the vector. This is the vector, let's say u plus v. Let's ignore the arrowheads for now. So this is something that represents u plus v, this line. And then this line represents u, and this line represents v, right? So this is how you define vector sum, right? So these three lines together form a triangle, right? These three together form a triangle, and the length of this side is norm of u plus v. The length of this side is norm of v, and this side is norm of u. Everyone, do you agree with this representation right now, whatever I'm doing here? Do you have any doubts in this, everyone? Please pay attention to this. This is a very crucial information that we need right now, right? This was u, this was v. Is this clear, everyone, what I'm doing here? So essentially you have two vectors, two arbitrary vectors in a 2D plane, and you want to find their vector sum, right? So this is how you use the parallelogram rule to find the vector sum, right? So essentially you draw the parallelogram that is formed by these two vectors, having these two vectors as two adjacent edges. So you can always define a parallelogram using this information. And then the diagonal from the origin to opposite end of this parallelogram gives you the summation between these two vectors, u and v, right? Now, what I am doing is from that parallelogram, I am taking the triangle that is formed by its diagonal and the top two edges. And the lengths of those edges will be something that I have written in shown in the diagram here. So the length of the diagonal will be equals to the norm L2 norm of the sum of two vectors u plus v, and one of the edge will be having norm one the norm of one vector, that is norm v. The other will be having norm of another vector, which is norm u, right? So this figure makes sense, right, geometrically. So this is the, because the definition is like this, right? Now I hope every one of you have seen one idea of one concept of triangle inequality, right? Triangle inequality that essentially says sum of any two, sum of the lengths of any two, any two edges is greater than equals to length of the third edge, right? So this means norm of v plus norm of u plus v has to be greater than equals to norm of u, or norm of u plus norm of u plus v has to be greater than equals to norm of v, or norm of u plus norm of v has to be greater than equals to norm of u plus v, right? So these three properties are from the triangle inequality, right? Why? You can always prove this. Look into this, the proof of this inequality. You will get to know that this is valid. And the second special case, right? This is one case. The special case, what happens at equality, right? What happens at equality, right? At equality, the triangle is degenerate, right? The triangle is degenerate, right? This means all the edges are collinear. By collinear, we mean all the edges lie on the same line, right? Fine. So this is the triangle inequality that we can use. And from here, we can always use this third property for our problem. So is, so from the third property, from 3, we can always say norm of u plus L2 norm of v, which is the edge length, essentially, the length of the vector, right? Norm of v is greater than equals to norm of u plus v. So it is saying always it is equals to. So for equality, they have to degenerate. So option A is not correct always, right? Not always, right? The second says u and v if both the vectors are in the same direction, right? So what do we mean by same direction? Option V. So it essentially says u plus v if u and v are in the same direction, right? If u and v are in the same direction. From this, what we can say? We can say u equals to some k times v, right? Because vectors represent a direction, right? Vector is nothing, just a direction in the space, right? So this means now if they both are pointing in the same direction, you can always say u is some scalar multiple of v, right? So let's plot this case. Okay. Mhm. Fine, right? Let me move things towards the left. Fine. So this was all about this, right? Hmm. Fine. So this was all about option one. So if at equality you are saying norm of u equals to norm of u plus norm of v equals to norm of u plus v. This essentially means the vector u. This is, let's say, vector u. Now then let's select vector v, and then u plus v essentially lies on this vector itself, right? So this is the meaning when you say norm of u plus norm of v equals to norm of u plus v, right? So option B, what it says, if u and v are on the same direction, right? So what does this mean? U can be written as kv. So let's say this is vector v. So vector u is essentially a scaled version of this vector v, right? And then u plus v is along this line, right? So this is the vector u plus v. And then this is true, right? This is always true. Option B is always true. So this makes the triangles formed by these three vectors degenerate, right? So the edges lie on the same line. Now option C, let's move on to the option C, right? U plus V if they are orthogonal to each other, right? Option C says norm of U plus norm of V if they are orthogonal, right? What does this mean? This means perpendicular, right? So let's say U looks like this and V looks like this, right? U and V. So no, again, we already saw through using triangle inequality. For equality, you need them to be or lie on the same line. So this is not the case. Option C is wrong. Option D, a number greater than u plus v. So option D essentially says norm of u plus v has to be greater than uh, norm of u plus norm of v. This is again wrong. This does not satisfy. This does not satisfy satisfy triangle inequality, right? Essentially, you can't form a triangle using the vectors u, v, and u plus v that satisfies this property, right? So option D is also wrong. Fine. Everyone, is this clear? So triangle inequality is very important property in used in linear algebra. This is one of the most basic and very important properties, yeah, that you will come across and you will be using everywhere for multiple proofs. So I hope this is clear. Everyone, is this clear? Great. So let's move on to the next question. Again, this is something that we have already done in the previous session, but again, since you have seen linear transformations such as scaling, rotation, and reflection in this week, I wanted to cover this problem again, right? So let's say this is your Cartesian plane formed by the basis x1 and x2, and you have a vector, any arbitrary vector, right? You have any arbitrary vector u that has the components u1 and u2, right? So I want to find the reflection of the vector u, a matrix that represents the reflection of vector, any arbitrary vector u, about the axis x1 in the x1 x2 plane, right? So this is the 2D x1 x2 plane. We are not allowed to move out of this plane, and I want to find the reflection of this vector u about the axis x1, right? So what will this reflection look like? So let's say if it's making theta from the x1 axis, then its reflection should also make some angle theta from the axis, right? So this will be the u reflected. So let me call it to u reflected, and let's write its component at u1 reflected and u2 reflected, right? And I want to find a mapping, essentially a mapping that transforms, gives me, that takes in vector u and gives out the vector v, right? How to do this, right? How to find this? Now, before proceeding this question, let's start with some idea. So now why I am saying this is a mapping, right? If I'm doing some matrix, I'm using some matrix, is it a mapping? So essentially everything that is related to a matrix product, right? Matrix 1 into matrix 2, this is essentially a mapping, right? This is a mapping which can be a function, right? Which is a function, right? So whenever you write, let's say you have a function of some matrix M, it essentially means you have some matrix product involved, right? So that's why we all sometimes call these as mappings, right? So how to find this matrix that when multiplied by u gives you u reflected, right? So we want matrix M, it's a 2 by 2 matrix, such that mu equals to u reflected. So find M, right? Find M. So everyone, have you seen the pattern of reflection matrix? I hope you have. Fine. So how to find this matrix, right? So easy. Let's just do some simple geometry and solve this problem, right? Now again, you can always say that this length on the x-axis, it grows on the length u1, right? And on the y-axis, it is capturing the length u2, this vector u, right? Again, u reflected will capture length u2 along the y-axis, right? u2 along the y-axis, and the same length u1 along the x-axis, right? So you can already write the value of uref, right? You know uref is essentially equals to, on the x-axis you go length u1, on the y-axis also you are on the x2 axis you are going length u2. but in the negative direction, right? So a positive is upwards, so negative x2 goes downwards, right? So this is taking length u2 along the negative direction, so minus u2, right? Now what you have to do, you have to set up a matrix m11, m12. So let's say this is the matrix entries, multiply it with u1, u2, and you should get u1 minus u2. What is the matrix that does this for us? Anyone? Can you answer this? Now, this is pretty straightforward problem. You can simply solve this problem very easily. Anyone? Okay, fine. So let me give you a hint. The hint is, you can say that this is essentially meaning this is equivalent to saying u1 multiplied by the first column vector of this matrix. So m11 into m comma 1 m2 u2, right? And then u2 into m12 comma m22, right? Now this is essentially equals to u1 minus u2. You are right. So answer is 1 0 0 minus 1. Why? Because the first entry remains u1. So essentially this means m11 has to be 1 and m12 has to be 0, right? And this gives us the first entry, and then again m21 has to be 0 and m22 equals to minus 1, right? When you set these entries, you get u into 1 0 plus u1 into 1 0 and u2 into 0 minus 1, you get u1 minus u2, right? So the answer is m is equal to 1 0 0 minus 1. So this is how reflection matrices essentially look in general, right? So this is the pattern where you will always find in a reflection matrix or a 2 cross 2 space in the 2D domain, right? If it's a rotation along x, you would have gotten minus 1 here and plus 1 at the bottom. So if you rotate it like this, x gets negated, y remains the same. If it's a reflection along the origin, both will be minus 1. So essentially it should have gone at the bottom, right? Everyone, can you say this? So just do a mental practice over here. What about if you want to rotate about axis x2 and then about the origin, right? About the origin. And from there, can you do it about any arbitrary line, right? Arbitrary line. These are three cases that I want you guys to think of, right? And let's come up with a solution to these cases also towards the end of the session. Till then, I want to move on to the next question. Do you have any doubts in this, everyone? I guess no one has any doubts. Fine. Let's move on to the next question. Question number 7, right? Okay. Isn't it x1 e1 plus x2 a2? Okay, so this, let me correct. So there is some mistake in this problem. Let me rewrite the problem here. So this essentially says, this is essentially, the problem says corresponds to any vectors is that, so says that x1 a1 plus x2 a2 equals to b for some scalars in b, for some scalars x1 and x2, right? For some x1 and x2, for some x1 comma x2, right? Then which the following graph illustrates. So what is the graph I'm talking about here is, so let me put in the graph here, right? So the graph is, okay, 1 2 3 4, okay, 1 2 3 4, and 3 4. See. right? So this is the E1 basis, this is the E2 basis, right? I and B is essentially 1 comma 1. This is our vector B. Then the vector A2 is uh, 1 comma 2 and A1 is 2 comma 4. 1 comma 2 and 2 comma 4, right? Okay. So this is vector A1, this is vector A2, right? Okay, so contain this size, let me zoom it. Hmm. Now this should be visible, right? So the problem is, I am saying that there is some scalar x1 such that x1 into a1 plus x2 into a2 equals to b for some x1 and x2. Then this is the graph that shows these vectors, right? So a1 is this vector, a2 is this vector. So this is the a1 vector, right? This is the a1 vector, and this is the a2 vector, right? So what does this system represents? Fine. Then everyone, can you see one thing here? Can you observe this? A1, the vectors A1, comma A2 are collinear, right? Collinear or point in the same direction. In the same direction, right? So the question is, do we have any pair x1 comma x2 such that x1 a1 plus x2 a2 equals to b, where b is not parallel to, b is not parallel to a1 or a2, right? Can we find any linear combination of these two vectors? Anyone? So this essentially means, so let me draw a simpler case for this. Right, this essentially means, so let's say you have this basis E1 and A2, and you have a line that goes from the origin like this, right? So this is your first line, and your second line is again this same line, right? And then you want to find, you have a point this. So can this point be a solution? Can this point lie on these two lines? No, right? You get zero solutions, right? Everyone, does this make sense? So since both line are coincident and the point does not lie on the line, you cannot have that point as a solution to the sum of these 2 points, right? So you a system with no solution, right? Option A is correct. Option B, C, D are wrong. Fine. So there is no scaling of the vectors A1 and A2 that will give you the result in their sum being the vector B. You will never find that any such scaling. Fine, everyone. Is this clear? So how do you do vector product? What you do, you form a parallelogram and go along across the diagonal. But if both the vectors are pointing in the same direction, you won't get a parallelogram. You will get a degenerate parallelogram kind of stuff, which is essentially the vectors are along the same line. The area is zero, right? The system is singular. Fine. Is this clear, everyone? Anyone, do you have any doubts? Okay, fine. Let's move on to the next question. So the eigenvalues of the matrix x equals to 1, 0, 0, 0 are, the question is, so what is the meaning of eigenvalues, right? So let's see something. Before starting with the answer, let's look into some concepts, some conceptual details, right? So what is the meaning of eigenvalues, right? Okay. So Let's pick up a matrix of our own choice. So I'm choosing this matrix. So let me define a matrix M that looks like this: 0.5, 0, 0, and 2 here, right? And let's pick up some vectors that I'm defining here. Just look into the vectors here, right? So let's choose this vector x1 that is essentially 1, 1. Choose vector another vector x2 that is 1, 0. Choose another vector x3 that is 0, 1, right? And let's look at the results, right? Mx1 is essentially 1, 1, so zero point 0.5 comma 2, right? Mx2 is essentially 0.5 comma 0, right? Or mx3 is essentially 0 comma 2, right? You can always do this matrix vector product and see this. Now, do we observe any pattern in this first equation, right? Can you say anything from equation 1? No, you are just saying that no equation, right? So this is essentially equals to 1 times the first column vector plus 0 time 1 times into the second column vector, right? But in equation 2, you can say that mx2 is essentially 1 by 2 times x2. Everyone, can you see this? Is this visible? Can you find this pattern here? So I'm just saying mx2 is equals to half x2, right? Then again, when you look at the third case, you will see mx3 equals to 2 times x3, right? Again, you look at this third case, right? You can find this. You will find this, right? Mx3 equals to 2 times x3. So from there, can we build up a pattern that says what are the vectors x such that ax equals to some scalar lambda. Let me take a scalar lambda times x for a given matrix A, right? So what are the vectors x such that ax equals to lambda x, right? So whenever you multiply that vector with a matrix, you get some scaled version of that vector, right? So these kind of vectors are known as eigenvectors, right? These are eigenvectors, and they are very important, very useful properties of matrices, and they give us a lot of information on the matrices, right? And the lambda values. What is the value lambda here? Lambda is a eigen value. What it says, it gives you the scaling, right? It is essentially the scaling factor, right? This is by the amount by which the vector is being scaled when it's multiplied by the matrix, right? So this is the basic idea of eigenvectors and eigenvalues. So whenever for a matrix, you can always find a vector such that when that vector matrix is multiplied with that vector again and again, the vector will be scaled in its own direction, right? So these are eigenvalues, right? Now again, this is the definition of eigenvector, right? So this is the definition of eigenvectors and eigenvalues. So the question is, we have a matrix 1, 0, 0, 0. So what are the, so you have to find what will be the lambda and what will be the eigenvectors, right? Right. So let's say it says ax equals to lambda x, and let's try to solve this. Ax equals to lambda x, fine. So this is a is 1, 0, 0, 0. X is x. Let's x say x1 is x1, x2, right? This is a, this is x, is equals to some lambda scalar into x1, x2. Let's try to solve this, fine. So this essentially means hmm, this essentially means okay. This means a, which is a, let's say a into, we can always rewrite this as lambda into some identity matrix, right? and this everything multiplied by the vector x, which is x1 and x2, right, equals to 0. Right. Now let's observe this system. Let's observe this matrix for a while and then proceed from here. Right. So what I have done is I took this lambda x1 and x2. So I have taken this, sorry, yeah, I took this term lambda x1 and x2 and I have written it as lambda times identity matrix, which is 1001 into x1 x2, right? And you can always do this since this is an identity matrix. You can always do this 1001, right? So any vector multiplied with the identity matrix ix equals to x, right? For any vector, this is a property of matrix multiplicative identity that is satisfied by all the vectors and matrices, right? That we are dealing with in this linear algebra course, right? And then I took it on the left hand side and took separated out x1 and x2, the vector x, as a matrix vector product. Now this is our new modified matrix, right? So what were the matrix here? This is matrix A, right? So let's call this matrix as M, right? Let's call this combined matrix as M, which looks like this. So 1 minus lambda, 0, 0, or minus 1, right? Multiplied by x, which is x1 and x2 equals to 0. Everyone, have you seen this system of equations earlier? Have you seen? So basically, if you remember, this is a homogeneous system of equation, right? Homogeneous system of equation, right? Now, first thing, when I was defining the this property, x has to be non-zero, right? If it's a 0, then it is satisfied by all 0 vectors, right? Has to be non-zero vector, non-zero, right? So x has to be non-zero. Now, how to get the solution? So what it means, so this means since it's a homogeneous system of equations, thus it can have either trivial solution, trivial solution that essentially means x1 equals to 0, which is equals to x2, right? So, or if non-trivial, if non-trivial, right? If non-trivial, then there can be many possible values, right? Many possible vectors x equals to x1, x2, right? Multiple values for x you can find, right? Now, since in the definition of eigenvectors, I have said that x cannot be a 0 vector, right? So we cannot have a trivial solution. This trivial solution essentially means x is 0, comma 0. We can't have this as an eigenvector. So the second only possibility is we can have multiple vectors that satisfy this criteria of being the eigenvector of this system, right? As the solution of this system, that will be the eigenvector of the matrix 1000, which is matrix A, right? Now, have you heard about the concept of null spaces? I hope you have, right? So there are two possibilities here. Number one, either either x is a 0 vector, right? X is 0 that we can't consider as eigenvector, or x lies in null space of matrix M, right? I hope you have heard about the concept of null space in a system of equations, right? This essentially means x satisfies so x lies in the null space of the matrix this matrix M. That essentially means all the vectors that you get. That means if you set determinant of M to be 0, you have to set the determinant of M to be 0. Why? Because if you want to have non-zero dimensional null space of the matrix M, you have to have, this is the important condition, right? This is the condition for having, okay, sorry, what's this? Right. So this is a condition for having at least one dimensional, right? One dimensional null space of M. That essentially means condition for having at least one non-zero vector such that mx equals to 0. Fine. So now for this condition, what should be the value of lambda? You can always solve. Determinant of m is 1 minus lambda into minus 1 minus 0 into 0 equals to 0. This gives you lambda equals to 1, right? You get lambda equals to 1. So there is the one possible case where you will get the eigenvector that is for lambda equals to 1. So 1 is an eigenvalue, right? 1 is an eigenvalue for this set term, for this matrix. And for that, you can always find the corresponding eigenvector also, right? Right. So, and the corresponding eigenvector, what would be it? It would be 1 minus lambda. So 1 minus lambda 0, 0 minus 1 multiplied by x1, x2. What is this quantity? Put the value of lambda equals to 1 here. You get 0, 0, 0 minus 1 into x1, x2, which is essentially 0 comma minus x2, right? So now you, since we for eigenvector we want that ax equals to lambda x, right? Ax equals to lambda x. We can always choose x as 0 and minus 1, a unit vector in that direction, right? So this is an eigenvector. Eigenvector corresponding to eigen, the only eigenvalue that we get 1, right? So essentially this can be plus 1 also, since we are dealing with only directions, right? So now let's look at the matrix A and finally what we have found achieved here. So we started with 1 0 0 0, right? So this was the matrix A here, right? And the eigenvector that we get is 0 comma x2, right? Okay, sorry. Yeah, I did a mistake here. Yeah, let me correct this quickly. Okay. Fine. So this has to be 0, right? We all know that this quantity a minus lambda I, this means a minus lambda I into x1, x2, which is equals to 0 comma minus x2. This has to be 0, right? This has to be 0 for the condition of from this condition, right? So you essentially from the condition of eigenvector existence, right? Now this means x2 has to be 0. Sorry. Yeah, x2 has to be 0 and x1 can be any value in the real number, right? X1 can have any real value, right? So for this, you can always define eigenvector 1 comma 0. So eigenvector 1 comma 0 and eigenvalue can be 1, right? And now you can replace this 1 with any real number and that will be an eigenvector of this matrix, right? So since we are dealing with one dimensional unit vectors, I'm choosing 1 comma 0. So now you see when you do 1 comma 0, you will get the answer 1 comma 0. So this essentially means a x equals to lambda x and lambda is 1 here, right? So is it satisfying this? Yeah, this is satisfying this, right? So this is how you find the eigenvectors for a matrix, right? So these eigenvectors are really useful in multiple analysis of matrices, fine. So this is the basic idea. Anyone do you have any doubts? Anyone do you have any doubts? Okay, fine. So now what I'm going to do, it's almost the session is almost over. So let's have a 15-minute session for question and answering. So if you guys have any doubts, please type in the chat box. The remaining questions I will cover in the next session. Okay, fine. So no one else is in the meeting. So yeah, I'll be here till 8. If someone comes, you can ask me questions, right? Fine. Otherwise, the session is over from my side.